Here are 25 key points about aerogels, drawn from the provided sources. 1. Aerogels are described as a special class of nanostructured, highly porous materials. 2. Despite their name, aerogels are solid, rigid, and dry materials. The name comes from the fact that they are produced from gels. 3. They possess unique features such as high specific surface area, very low density, often described as 95% air or ultralight weight, hydrophobicity, low thermal conductivity, and optical transparency. 4. Aerogels have a three-dimensional, highly porous structure, often composed of spherical particles fused into clusters forming almost fractal chains. 5. The pores in aerogels are typically just under 100 nm. 6. While silica aerogel is common, aerogels can be made from various materials including carbon, metal oxides, synthetic polymers, and biopolymers. 7. Aerogels are produced using sol gel technology, a method involving precursor preparation, aging, and drying. 8. The drying step of the gel is considered the final and most critical step in the production process of aerogels. 9. If the liquid in the gel is allowed to evaporate naturally, ambient pressure drying, capillary forces can cause the gel network to collapse, resulting in materials known as aerogels, which have lower porosities and significant shrinkage. 10. To prevent the collapse of the gel structure during drying, techniques are used to minimize surface tension within the pores. 11. One primary method to avoid capillary tension is supercritical fluid extraction, where the liquid is removed above its critical point, where the distinction between liquid and gas disappears. 12. The first documented aerogel was created by Samuel Stevens Kistler in 1931 using a process known as supercritical drying. 13. Another drying method that avoids capillary tension is freeze drying, lyophilization, which involves replacing the liquid with gas by sublimation along the sublimation line. 14. Supercritical drying can be carried out at high temperatures, HTS-CD, or lower temperatures, such as the Hunt process, LTS-CD, which typically uses liquid carbon dioxide after a solvent exchange. 15. While highly effective at preserving porosity and minimizing shrinkage, supercritical drying can take several days, requires specialized high-pressure equipment, and may involve safety hazards. 16. Ambient pressure drying, APD, is a less expensive drying method, but it typically requires chemical modification like silylation to make the aerogel hydrophobic and prevent collapse caused by capillary tension during evaporation. 17. Due to their remarkable properties, silica aerogels have potential applications in areas like thermal insulation, sound absorption, adsorption, flame retardation, sensing, and catalysis. 18. The high porosity and specific surface area of silica aerogels make them suitable for environmental filtration and for adsorbing toxic molecules. 19. Aerogels are being increasingly explored for a wide range of applications including food, controlled release, biomedical, tissue engineering, wound healing, drug delivery, textiles, thermal insulation, protective clothing, packaging, energy storage devices, ultracapacitors, batteries, aerospace engineering, and environmental remediation. 20. Polyimide aerogels are highlighted as being much stronger than silica aerogels at comparable densities. 21. Although aerogels are nanostructured materials, their classification as nanoforms is ambiguous according to some definitions, which presents challenges for developing legislative frameworks. 22. Currently, there is a lack of specific exposure limits identified for aerogel products. 23. Despite the lack of specific aerogel limits, workplace exposure limits for amorphous silica, a common component, exist in various countries. 24. Recommended safety practices for handling aerogels include avoiding dust cloud formation, using local exhaust ventilation, adequate general ventilation, and wearing personal protective equipment such as protective glasses with side screens. 25. The development of safety regulations and best practices for the production, handling, transport, and end use of aerogel-based formulations is crucial to mitigate potential human and environmental risks.